Let's say you have an awesome gadget that uses a USB connection to charge its battery or simply uses USB power directly to work properly. In both cases, a so-called USB power meter can be a useful tool to measure the voltage of the USB port, the current your gadget draws, the power it thus needs, and most importantly, it also logs how much energy is transferred. This way, after converting the value to kilowatt hours, you can simply multiply this value with the price per kilowatt hour and therefore, for example, calculate that wireless charging your smartphone costs you 0.15 euro more for every 100 charges. Now of course you can get such a power meter for cheap on eBay. But in this video I will show you how to create your own portable upgraded version which has a wider voltage range, a higher measuring frequency and even SD card support in order to evaluate your measurements later on. Let's get started. An Arduino Nano will be the brain of the organization for the first prototype. Measuring voltage with it is as simple as connecting the positive terminal of your loads to an analog input, the negative terminal to ground, and writing a simple analog read command. But measuring current is definitely a bit more complicated. Commonly, you would need a current shunt, which is basically a precise low-value resistor, that needs to be placed in series to your loads in order to create a voltage drop proportional to the flowing current. This voltage drop can then be amplified and fed into a microcontroller in order to calculate the current value. But in order to make life easier for us, let's simply use the INA219 bidirectional current power monitor IC. I got mine embedded on a PCB for only $2 from eBay, which also includes a supposedly 0.1 ohm current shunt and a screw terminal. Due to the maximum current shunt input voltage of 320 mV, we can measure a maximum current of 3.2 amps and a maximum voltage of 26 volts. Hooking up the IC to the Arduino is the same procedure as with any other I2C device. Serial data connects to A4 and serial clock connects to A5. At this point we could use the wire library of the Arduino to write our own I2C code in order to communicate with the IC. But we could also just download the INA219 library from Adafruit, include it and write way fewer lines of code in order to output the current and load voltage through the serial monitor. In order to measure anything useful though, we first need to connect the V+ pin to the positive terminal of the supply voltage, the V- pin to the positive terminal of the loads, and the ground of the loads to the ground of the measuring system. Now the serial output delivers pretty accurate values, which means we can continue by using 3 more variables and the millis function in order to let the measurement repeat every 100 milliseconds. This way I can not only add a power measurement output by multiplying the current and load voltage, but also an energy counter, which adds the power value multiplied by 100 milliseconds converted into hours to the previous energy value. Since the serial monitor now presents all the values we care about correctly, it was time to add a display to the circuit. In this case a 0.96 inch OLED LCD, which I got from eBay for $4. The wiring was exactly the same as before, since the LCD also uses the I2C communication protocol. After downloading and including the library for it from Adafruit, it was simply a job of using the print line function and figuring out where to position the text on the LCD in order to make it look decent. And for many people this setup should already fulfill their demands for a power meter, but not for me. That is why I got myself a commonly available Micro SD Card PCB, which can be found for $2 and also includes a LVC125 level shifter IC. This IC is important because the SPI pins of the Arduino 11 to 13, to which the SD cards needs to get connected to, have a high voltage level of 5 volts, but the SD card can only handle 3.3 volts. And don't worry if you missed a step during the wiring of those components, because I utilized the Easy EDA free circuit design software to create an appropriate schematic beforehand. You can find the link to it along with other project information as always in the video description. Now after formatting the SD card and plugging it in, we could use the SD library, which is always included in the Arduino IDE, in order to write to it. But I have to say that I had quite a few problems with it while trying to open the files. I rather recommend the SDFAT library, which uses the same commands but does function without a problem. With it, the SD card creates 3 text files which contain the time, voltage and current values. By simply importing them into a program like Excel, you can then create decent looking graphs and of course also calculate the power and energy values. Last but not least, I removed the used components from the breadboard, replaced the Nano with an Arduino Pro Mini, which I programmed with an FTDI breakout, added a LiPo battery with protection/charging circuit to the system, soldered everything onto a piece of perf board and connected the components to one another. Of course, you can create a beautifully crafted enclosure for your power meter, but mine does not really need one for what I have in mind for it. And with that being said, this project is complete and works like a charm. I hope you liked this video. As always, don't forget to like, share and subscribe. Stay creative and I will see you next time.